Okay, so now let's do the simple transverse shear stress example, and we know this one will give us the introductory knowledge we need to know to solve any of these types of questions, applying that transverse shear stress equation. So what we have here is we're told the simply supported beam shown is subjected to two concentrated loads of 1200 pounds and 600 pounds. The rectangular cross-section of the beam has a width and height dimensions of 2 inches and 8 inches respectively. The maximum shear and stress in PSI in the beam is most nearly what? So what we're given is a simply supported beam. Simply supported meaning it has a pin on one end and a roller on the other end, subjected to two concentrated loads of 1200 and 600, 1200 and 600. These are the external loads, point loads, and we have a rectangular cross section for the beam, right? And it has essentially that width dimension, which is like the base of a rectangle, is 2 inches if you look at it from this view, and the height here is going to be 8 inches for the cross section of the beam. So we want to find the maximum shear and stress, right, in the beam, the maximum shear and stress. So let's write that as what we want to find. We'll call it tau max, because we know we use tau for shear stress, right? We use this symbol for shear stress, and we want it in PSI, pound per square inches. So we're given actually everything in the problem statement, right? We're given the dimensions, we're given the loading. So let's just quickly dive into that solution. And what do you suggest we do? So how would you actually solve for that tau max, the maximum shear stress, basically transverse shear stress in the beam? And I want to say, when they say transverse, all we're talking about here is you have the beam. So let me actually draw that. You have like a beam here, and for this beam you would have like a shear stress, and that transverse direction meaning it's going to be in this direction. So we find that shear stress, right? This is the shear stress that we're going to solve for. Most importantly, we're going to find the tau max, right? The maximum tau max. So what we can do is actually just use the FE handbook equation, right? The transverse shear stress equation, and it's going to be under what section? The stresses in beams. Stresses in beams. So it's a whole section. If you do Control F or Control Shift F, it should come up as a section. You type that, stresses in beams, and it has the normal stress, but that's not what we want, right? We do not want that maximum normal stress or the normal stress at any location. What we want is the shear stress, the transverse shear stress. So let's write that equation first. So we're going to say that tau max is going to equal to the VQ divided by IB. So here V is going to be the shear force, right? V is the shear force. Q is the first moment of area, and we know I is going to be the moment of inertia. Then B is going to be just simply the width of the cross section. So B in this case is quite simple. It's just 2 inches, right? But we know here that let's work one by one. So let's take it one by one. Let's look at V. So V is the shear force. Here, we're not really given an exact value, right? We're not given that shear force. So we do not know. We do not know that shear force. But one big hint is they're telling us you want to find the maximum shear and stress. That tells me, okay, the maximum shear stress occurs when we have that maximum shear force, that maximum vertical shear force. And how would we get that shear force? From the shear diagram, right? You have that shear moment diagram, but all we're going to do here is look just strictly at the shear diagram and get the maximum value for the shear force, drawing that shear diagram. So if we draw the shear diagram real quick, in this case we're given all the loads, right? You're given the reactions, so you can do that real quick, right? We can do that, and what we can do is just draw the beam here, and we know we have the reaction here is 800 and the reaction here is 1000. Those are given for like a FE type question. This is 1200 and this is going to be 600. So you just draw that shear diagram. So if I draw that here, 0 is going to be this axis, and we know that 0 is this, and we're drawing the shear force, let's call it V, and the units will be what in this case? Pounds, right? Units of pounds. So at this end, you start from left to right. So we start here, and we know at this, where we have A, that pin, it tells us go up. The arrow points up, so we just go up how much? 1,000, right? 1,000 pounds. You go up 1,000. So we're starting here. We go up 1,000. Then we move across. We notice nothing's happening, right? Picture you moving there. Nothing's happening. So you just stay flat. So it's just going to be constant. So it's constant all throughout. Constant, 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 until we hit this 1200, which is essentially here at B. And at that 1200, it tells us go down 1200. From where? The 1000, right? From that, the point we're at, which is 1000, go down 1200. And that brings us to what? It's going to bring us to negative 200. So that brings us down to negative 200. So it's just a vertical line to negative 200 pounds. So now we are essentially here, right? And then we keep moving, nothing's happening. So we just stay flat. Flat, flat, flat. But here we notice we hit that 600. That tells us go down 600. From where? The negative 200. So you take negative 200 minus 600, and that gives us how much? Negative 800. So that's just vertical, negative 800. Then now you move across, cross, cross, and we end here, right? So flat, 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 flat. And then this tells us it points up, so it tells us go up positive from the negative 800. So we're at negative 800 here. We add 800 and we end at 0. That's how we, that tells us like we did this thing right when we end back at 0, right? So now this is the shear diagram, and all we do, just like what we stated, you just take the max value. So this is actually the V value. This is going to be the V value we use. It's the maximum value of 1,000 pounds. Because we want to find, once again, the problem statement says maximum shear and stress. So use your maximum shear and force. So that's the V value you would have to use, right? That 1,000. And that's what we're going to put in there. So we took care of that, right? That one's done. So now, let's move on to the next one, Q. So Q can be complicated. Q can be complicated, and we'll learn it for this simple example, but you can apply the same procedure to I-beams, trapezoid shapes, circles, or T-beams, non-symmetric I-beams, and so on. But this one's going to be relatively simple, right? Because you just have a rectangle and it's symmetric about the middle axis. And that middle axis is also called the neutral axis, the middle axis. So now, we know we need to find Q. And in the handbook, it says Q is the first moment of area above or below the point where the shear stress is to be determined. So that's going to be Q. So let's write the equation. It's the first moment of area. It's going to be A prime times Y prime bar. So it says, be careful with the wording. It actually tells you what to do in that statement. It says, first moment of area above or below the point where the shear stress is to be determined. So now, you're like, okay, where the shear stress is to be determined. Where is the shear stress to be determined, right? If you look at the cross-section, let's focus on the cross-section. Where is the shear stress to be determined? Where the maximum shear stress occurs. So now you actually have to think about that stress distribution, the shear stress distribution, not the normal stress distribution. That's different. We look at the shear stress distribution, and we know the shear stress distribution for a simple shape like this is just going to be parabolic, and its maximum at the neutral axis. And if I draw that for us, it looks something like this. So let's say we start, this is like where we have 0 here, 0 here. We draw a parabola, right? You draw that parabola. You draw the parabola, which should be, it should be symmetric. So this thing should be symmetric. About what axis? The neutral axis. So this is the neutral axis. This whole thing is the neutral axis. We'll call it NA, neutral axis. And what's interesting is the maximum shear stress occurs at that neutral axis. tau max, which is what we want to find. Here at the top, at this top, and at the very bottom, like at the edges, it's 0. Tau is 0. And you can, like, if you picture the normal stress distribution, you can pause the video and try to draw that or Google it. It's basically the opposite, right? Because at the top fibers, the normal stress is actually maximum, right? The compression, well, if you have, in this case, positive bending, you have the positive on top. So you have the compression on top and tension on bottom. So it's actually like the opposite, right? The opposite. And that one's actually linear, right? For the normal stress distribution. When we find the moment, right? When you find the maximum moment. And when you use the normal stress equation. But note that at the bottom and top, the tau is 0. Tau is 0, and this is your stress distribution. Again, at the neutral axis, it's maximum. The shear stress, the transverse shear stress. So this is what we have, and that's how the stress distribution looks like. And I want to write, we said it's parabolic, right? Parabolic. It's a parabolic distribution for the shear stress for a simple shape like this one, which is going to be a rectangular beam in this case. So now that's going to be that. And now, okay, we know where that point is, right? We know it says above or below the point where the shear stress is to be determined, the first moment of area. We know where the point is. It's going to be there. It's going to be at this point, right? Because that's where the maximum is. So now all you have to do is pick an area above or pick an area below. And here they're just the same, right? So what we're saying is we know the maximum shear stress occurs here. That's the point where it is to be determined, right? That's the point where we want to find it. So we pick an area above that, whether it may be this area, or you can pick the bottom area. They're the same, right? They're going to be the same areas. And think of this as like taking the whole area. You start here from 0, you take the whole area until you get to the maximum, right? So you take this whole area. Or you can do the same here. You start at 0, take the whole area until you get the maximum. You can use that area. Above or below, right? Above or below where the shear stress is to be determined, which is at the neutral axis, again, because we want to find that maximum shear stress. So here, I'll just use the one above. It's actually the same in this case. But that's going to be the area that we're going to look at. That's going to be the area. And let's actually find the area. That area is actually the A prime value. That's going to be the A prime. And for A prime, you just take the area of that shape, right? So the area for that shape, we know this dimension is how much? We know the whole thing is 8. That has to be 8 divided by 2, which is 4 inches. That's 4 inches. So the area of this shape is just 2 times 4, right? 2 inches times 4 inches, which is 8 inches squared. So now we're done with A prime. So we just found A prime, right? We found this. Now Y prime bar, that's actually defined, right? It's going to be the distance from the neutral axis to the centroid. Distance from the neutral axis to the centroid of the area. Of the area we denoted in blue here, right? Distance from the neutral axis to the centroid of the area. So now let's actually denote the centroid of the area. Let's call it here. That's going to be the centroid of the area, which is like that center, right? It's just 4 divided by 2 from the top and 4 divided by 2 from the neutral axis. So it's going to be this distance actually, right? That distance, Y bar prime, is going to be this distance. It's going to be that distance to the centroid of the area that we're looking at. So that's going to be Y bar prime. So Y bar prime. And that's going to be how much if you actually find that? You just take 4 divided by 2, right? Take 4 divided by 2 and you get 2 inches. That's going to be 2 inches. So now we're done, right? That's going to be the first moment of area because we have A prime, we have Y bar prime. So Q, let's actually solve for that. So A prime is going to be how much? A prime, we said it's 8 inches squared. And you multiply by the Y bar prime, which we said is just the 2 inches, right? That's going to be the 2 inches there. And notice how inches squared times inch is going to be inch to the third. Those are the units for Q, the first moment of area. So you take 8 times 2 and you get 16 inches to the third. And that's what we will plug in there. So we're done with Q. We're almost done. I in this case is what? How would you find I for a rectangle? You just use the statics tables, right? And in this case, you have bending about the x-axis. Well, the neutral axis. You have bending about the neutral axis in this case. The neutral axis being that, which is actually like the x-axis. And you can picture it like, in this case, if I redraw this thing, you have like a beam that's trying to bend about like the axis, which is like the neutral axis. And it looks something approximately like this, right? So it would look something like that. And you have bending about that neutral axis, which is going to be this way. This is our neutral axis, which is going to be the x-axis. X-axis. So we have bending about that neutral axis, the x-axis. And we know you just use IXC, right? IX, the one for IX. So for that one, if you look in the statics tables, you do base times height to the third divided by 12. Base times height to the third divided by 12, and that's going to be the I value. So base times height to the third divided by 12. So the base, you put 2 inches. The height is going to be what height? It's just the total height of the rectangle. So 8 inches to the third divided by 12. So now, doing the math for that, you should get about 85.33 inches to the fourth. So that's going to be the first moment of inertia. Sorry, the moment of inertia, the I value. Now for the B value, that's going to be quite simple because B is just the width, right? It's just 2 inches. 2 inches for B. And we're done. So you just solve for tau max. So tau max equals to the V value. Again, what's the V value? Don't use the maximum like external load. That's a typo, and it's actually in here if you put that, but it's going to be the 1000, right? Put that 1000, the maximum shear force, 1000 pounds. Q is going to be the 16 inches to the third divided by the I value. The I value is going to be this, 85.33 inches to the fourth. Then you multiply by the B value. The B value is how much? The B value is going to be the width, and that's going to be 2 inches. So now we solve for tau max. And if you do that, so let me do the math. You do 1000 times 16 divided by 85.33, and you multiply by 2. And you get 93.75. So it's about 93.8. And you should get PSI, right? You get PSI because the inches to the third here over inches to the fourth, this actually cancels. This just has a 1, right? If you take the 3 over 4, you have that 1 left. So inches to the 1 is just the inch. Times the inch is inch squared. You get pounds on top. Pound per inch squared is PSI, right? So that's going to be the answer for this one. So 93.8 PSI, and that should be A for this. And I want to say real quick, some of you might have already known this, probably the mechanicals. You could have just actually used an equation that's not in the handbook to check your answer. But obviously, okay, I want to say that you have to know like the steps here, right? You have to know the procedure behind how you would do this, just in case like you get a T-shaped beam or an I-beam that's like non-symmetric. Or if you have a symmetric I-shape, there is an equation, but that's going to be, it's the accuracy is like 15% off. So it's 15% lower than what you would get if you actually did the calculation. But here, if you just use this equation, you would get the same answer. So this is for a rectangle. Any rectangle, you can just use this equation. you take 3V divided by 2A. And A is just the area of the cross-section, the total area. So let's do that. You take 3, what's V? V is still the value we got, right? That 1,000. So you would still have to do that step. So that's going to be 1,000 pounds, the maximum shear force. 2, what's the area? The area is simply, in this case, the 8 times 2. So it's 16 inches squared, the area of the whole section. And if I do that, let me check. We should get the same answer. It should be exact because this one's actually exact. And when I do that, I get 93.75. So it's, yeah, 93.8. 93.75 psi. So this would save you a lot of time if you do indeed have a simple section like this one. But this one's like to give you the foundational knowledge that you would, giving you the exact steps of analysis, right? Just in case you do not get such a simple shape. Like a rectangle, you might get a non-symmetric I-beam, a T-beam, whatever it may be. But you can indeed like just use this, right? You wanna, I would probably memorize this for the FE in case you get such a simple question. You can check your work, or you can actually just apply this and move on to the next example. And I think that's it for this, and thank you.